I'm really excited to be here. So we're going to start with a few questions. Raise your hand if you code in Java. Awesome. Okay. Who here works with caches? Okay, keep your hand up if you've broken production before. Awesome. Okay, so raise your hand if you built a cache so big, you broke production with it 3 times. Okay, hi, I'm Shelli Glick. I'm a software engineer in Taboola's infrastructure group. And today I want to tell you the story about that very big cache. So it was a while back, and my manager handed me this black box. He told me it's called the Creator. He said it's decades old, and that no one's opened it in years. He wasn't sure what's inside, but he wanted me to make it run faster so we could increase our revenue. And just to understand what Creator is, let's talk about Taboola. So in case you haven't heard of us, you probably used us, or at least seen us, and just weren't aware. Taboola is the leading content recommendation company in the world. And our challenge is at any given moment, find the best recommendation for you out of the billion options that we have. And so the way it works is, while you're on your phone looking for something interesting to read, a request is sent to our servers for a recommendation. We then have to go through our entire inventory of items and using all kinds of fancy algorithms, find the best one for you. The thing is, our inventory has over 1 billion items we could choose from. And we get such requests over 500,000 times a second. And our response time has to be under 200 milliseconds. Under 200 milliseconds. Okay, now all these numbers together are a problem, right? And that's where the Creator comes in. Creator is a service running in the background, going through our entire inventory, and for every context, select the top items, and then stores them as a list to Cassandra. So basically, when we get a request to our servers, instead of having to go through our entire inventory of items, we can just go through that list that the Creator prepared for us in advance, right? Basically, the Creator reduces the problem from 1 billion items to only 10,000. And what we're going to talk about today is how we made Creator run faster. And why do we even want to make it run faster? So Creator's running in the background, generating these lists of top items for a given context, and these lists are a core part of our flow. So with no lists, no recommendations, right? The thing about these lists is they could take hours to generate them. So if Queen Elizabeth dies, and we talk about it only 8 hours later, well, it's not so good, right? So that's the theory, data freshness. If we can make Creator run faster, we can improve the quality of our recommendations and increase our revenue. So to understand what it means to have Creator run faster, let's talk about how Creator operates and align a few terms. A Creator cycle fetches relevant data, runs a lot of heavy computations to find those best items, and then stores them as a list to the database. A Creator task is what defines the Creator cycle, defines the data and the setup the cycle should handle. Creator tasks all sit in a queue, each with a different priority. They can wait in the queue for minutes, hours, and some even wait there for days. A Creator thread is what takes a task from the queue, runs the cycle according to the task setup, and once the cycle is over, it puts the task back in the queue to be run again later. So we have 2 main factors that impact our data age: how long it takes a cycle to run, and how long tasks have to wait in the queue. So Creator's doing a lot of work, complex computations on a large amount of data. And so it runs with a machine that has 200 cores and 2 terabyte RAM times 50. 200 cores and 2 terabyte RAM times 50. So Creator's running on monster machines, doing a lot of complex work, millions of lines of code. We don't even know how it works. So in theory, making it run faster sounds nice, right? But it's a complex problem. And so we need justification. We needed data to prove our theory. Now, in order to measure the impact making Creator run faster has on our revenue, we have to actually make it run faster, right? We don't know how to do that. But what we can pretty easily do is make it run slower. Now, Creator tasks have different task durations. Some take minutes, while others can take hours. So we took only those tasks that take a few minutes. We then gave them different simulated delays. And then we ran an A/B test over those delays. We then got data points showing us, for each delay, how much revenue we lost. And what we saw was, the higher the delay, the higher the revenue loss. So we took these points and turned them into a formula. The formula takes minutes and turns them into potential revenue uplift. And so we proved our theory. If we can make Creator run faster, we'll have a good impact on our revenue. Okay, so we have motivation. TLDR, we want to make Creator run faster so we can increase our revenue. So in order to do that, we have to understand Creator's performance, find its bottlenecks, but we're not really familiar with how it works. So where do we start? But what we do know is it could be one of three things. We either have something taking up a lot of CPU time, but we see that's not the case. Our CPU usage is low. So it could be that our heap is full, and we're very busy doing a lot of GC, right? Well, it's not the case either. We're not spending that much time in GC. And so what we know is we're probably waiting for something else, right? So in order to find what it is that we're waiting for, we ran a Java profiler. Now, there are different profilers out there that we could choose from, but we decided we like to use Async Profiler for various reasons. First, it's open source. It has a low overhead due to the fact that it's only a sampling profiler, meaning it only samples the Java stack traces. It doesn't actually record all the events by instrumenting bytecode. And last, it avoids what's called the safe point bias problem. And we're not going to get into what that means now because it's a whole other topic. What's important to know is that Async Profiler's final result is more accurate. So we can run it in different modes. We can run it in memory allocation mode to see where our memory bottlenecks are, CPU mode to see what's taking up CPU, or wall clock mode to see what our threads are doing over time. In our case, we knew that our CPU wasn't the problem and neither was memory. And so we ran it in wall clock mode to see what our threads are waiting for. Async Profiler provides out-of-the-box flame graph support, basically a visualization of your thread's traces in an interactive HTML. So you could search, you could zoom, and importantly, you could see the duration threads are spending on each trace. The way it works is that yellow is C++, green is Java, orange is the kernel, and red is the remainder. And the more amount of time your threads are spending on a trace, the wider it'll appear in the flame graph. So you want to look for those wider parts and read it bottom up. So we ran Async Profiler over the creator. We opened the flame graph, focusing on those wider parts. And we found 60% of its time, it was making I/O calls to another service. It was making 8 million calls a second to another service running TensorFlow. So it seemed to us like a very hard problem. How can we make Creator run faster? We don't even know what's inside. Well, it seemed pretty easy now. Let's build a cache over the result, right? Creator will be running twice as fast. So we built a plan. We had a design meeting. We told everybody about the cache we plan to build. We told them it'll be a few days and Creator's going to be running twice as fast. What could possibly go wrong, right? So the cache design was something like this. Under the hood, we'd be running with a simple Guava cache with a simple TTL expiration policy. And our cache key'd be composed of a long and a byte array. But hold up. There's something wrong with our solution, right? I don't know if you followed, but our goal was data freshness. So how can we cache some result, which by definition is a compromise over freshness? So there's something special about our setup. Our TensorFlow service goes through a version upgrade only every few days. And every version is guaranteed to be deterministic, meaning we could send the same input to it as many times as we want, and we'd always get back the same result, as long as the version wasn't upgraded. Okay, so instead of having a TTL expiration policy, which is key-based, we had a full cache invalidation and recreation every time the TensorFlow service version was upgraded. The pattern was something like this. The cache size would slowly grow until the TensorFlow service version was upgraded and it'd be invalidated and we'd start again. So let's just have a short recap. So we spoke about Creator. It's a backend service generating lists of top items for a given context. We want to make Creator run faster so we could improve the quality of our recommendations. We don't know how it works, so we ran an async profiler to see what it's doing, what it's waiting for. We found it was making 8 million calls a second to another service running TensorFlow, and so we decided to build a cache over the result so we can make it run twice as fast. And what was special about our cache is that every time the TensorFlow service version was upgraded, we'd invalidate the entire cache and start again. Cool, right? It was 3 a.m. and we got a call. Creators are dying one by one and we're losing money. Panic, right? Okay, so we look at logs, we look at metrics, we try to see what's going on. We find the process is still alive. It's just not doing anything. And so eventually we see it's just busy doing GC. We then see this, a picture of our heap dying. The blue line here is the free old gen space, slowly disappearing. So we knew it could be one of two things. Either our cache grew so much, it's taking up all of our heap, or we have a memory leak. So to figure out what's going on, we have to see what's inside our heap. And so we wanted to take a heap dump. We wanted to see the number of instances each class has in our heap, its shallow and retained size, its shallow size, how much space the object itself is taking up, and its retained size, how much heap would be freed once this object goes through GC. The thing is, the retained size, it gives us only the final number, how much retained size. And so what we need is the dominator tree, which gives us the object graph explaining the retained size. And so we see where all the heap is coming from. So cool, right? Let's take a heap dump. We can't. I mean, we can, but with a heap 2 terabyte large, we can take a heap dump, but we don't have a machine with large enough RAM to actually open it on and analyze it. And so we were left with taking a memory histogram, which is a more lightweight version. It only gives us the number of instances each class has on heap and only its shallow size. So it's not as good, but it's what we got. So actually, the first time we tried to take the memory histogram, we failed. We didn't even have enough space on heap to just do that. So we had to restart the service to free up the heap, and we configured a periodic job to take the memory histogram once an hour. Being that now it was periodic, we were able to build a pattern over time of what our heap looked like, and so we could see if something looks off. We took these periodic dots of how many cache keys we had, and we put them into a graph. We saw the number of cache keys just keeps growing over time. And that correlated with our free heap going down over time, right? So it looks like our cache is just too big to fit. Well, no. We have application-side metrics. And we can see our cache is going through invalidations. Its size is going up and down. And so now we know we have a memory leak. And if we take an even closer look at these numbers, our application-side metrics are showing us our cache size, its previous size, was just over 300 million entries. Our current cache size is 240 million entries. And if we put these two numbers together, we get the exact number our heap histogram is showing us we have in heap. Meaning our heap contains the entire current cache and the entire previous cache that we already invalidated. So we went to look at our cache creation code and found these. we had lambdas registering both configuration listeners and metrics to our cache. And the lambdas were holding a reference to our cache and keeping it. And so even once the cache was invalidated and we created a new cache, the lambdas were still holding a reference to the old invalidated cache. And so GC never saw it as garbage and never freed the heap. We all felt kind of funny about it, but we learned two things. Even when we can't take a heap dump because we don't have enough memory to open it on, we can take a memory histogram, which is more lightweight, and even better if it's periodic. In addition to that, lambdas aren't innocent. They keep a reference to the object that you're passing to them, and so you have to be aware of that. Anyway, we fixed the code, the leak was over, and things were looking better. Right up until, again, it's 3 a.m., again, it's creator dying, and yes, again, it's the heap. Except this time, all the numbers added up. We didn't have a memory leak. This time, our cache was just too big to fit in memory. So we did the easy thing. We limited its size, and the issue was over. The problem is, the metric that usually correlates with cache size is cache hit rate. And by limiting the cache's size, we limited our hit rate as well and lost the cache's effectiveness. So we're back to square one. Again, creator is spending 60% of its time making IO calls to another service. Our cache isn't effective due to its size limitation. So we went to our whiteboards, looked at our cache data structure. We knew we had to reduce the memory footprint of our cache so that it could hold more entries and have a higher hit rate. Looking at the data structure, our cache key composed of a long and a byte array. We found that while our byte array had millions of distinct values, our long had only 200 distinct values per creator instance. And so we were able to migrate the long to an integer due to the low range of values. Now you could say these are only 4 bytes distinguishing longs from integers, but they appear on every row of our cache, which could have 1 billion rows. So we're just talking about saving gigabytes. And if we take an even deeper look at our data that our cache is holding, we know that now our integer has only 200 distinct values, but each one of them appears millions of times in our cache. And so it'd be a lot better if we could save only a single instance of each value, right? So we split our cache into 2 layers, an outer layer with an integer as key, holding only 200 rows, and an inner layer, a byte array as key and a double as value, with millions of rows. Basically, we went here from having 1 billion longs to only 200 integers. 1 billion longs is 8 gigabytes, but these aren't even primitives, so it's a lot more than that. So we're happy with our data structure and the object we chose. We now went to look at our collection, and we wanted to use a Trove collection. Trove is a Java collection library. Its goal is to reduce memory footprint while maintaining performance, and it does so with 2 main features. So the first, Trove uses primitives instead of wrapper objects. For example, it would keep a long primitive on the stack, taking up only 8 bytes, instead of keeping a wrapper long object, taking up space for a reference on stack and space on heap for the object, composed both of the value and the header. So obviously, when you're dealing with large amount of items, it has a major memory impact. The second thing that's special about Trove is its addressing method. Most JDK collections used what's called chained addressing method. Basically what this means, on the hash table itself, each slot holds a linked list. And then on a collision, the element is added to the linked list. So at times when you're searching, you traverse these linked lists until you find the element that you're looking for. On the other hand, Trove uses what's called open addressing method. Basically, it means that all elements are stored in the hash table itself. And in on collision, there are different techniques to find the next available slots. So by doing this, Trove reduces memory by avoiding the linked lists. You have to keep in mind, though, that in general, open addressing is more sensitive to collisions. So you have to make sure you have a good, it's not working. You have to make sure you have a good hash function that's both efficient and has a good keys distribution. And you want to make sure your load factor is low, because once the number of items starts getting close to the size of the hash table itself, you start suffering from performance degradations due to these collisions. But if we sum it up, Trove reduces memory footprint by using primitives instead of wrapper objects and by avoiding the linked lists. And due to these two things, many applications will actually experience a performance gain because they avoid all the overhead of objects like boxing, unboxing, creating and maintaining new objects for each entry in the map. So it all sounded nice in theory, but again, we're looking for more data. So we tried to calculate these numbers, but we weren't feeling very confident. So we tried Google only to find out multiple different answers. In addition, we knew we had to take more things into account, like the system architecture and the JVM padding. Eventually, what we did was to write a few lines of code locally and take a small heap dump. We found that if we use a Trove collection, every entry would take up 20 bytes. But our current implementation, every entry took up 100 bytes. So success. We reduced the cache size by 80%. Our hit rate was now high. Creator now was running much faster. So if we go back to the two things that impact our data age, we talked about the cycle duration, which we improved by 50% by adding this new cache. We now wanted to reduce the amount of time tasks are waiting in the queue. And so we wanted to increase the number of threads. In order to do that, we went to look at its CPU metrics to see if it could at all handle more threads and more work. We found that the CPU usage was low. So happily, we increased the number of threads, only to once again, our heap. The thing is, threads aren't for free. They require resources, both RAM and CPU. Especially creator threads. They're not lightweight tasks. They're heavy computations involving a large amount of data as input. In our cache, it was taking up all of our heap. And so there was no more space left for these threads. And so we were stuck with underutilized cores. So once again, we knew we had to reduce the amount of space our cache was taking up on heap so that we could increase our throughput. But this time, trying to optimize our slim data structure, well, it didn't look very promising. So we're stuck in an awkward situation. We have a good cache. It has a high hit rate. Creators running fast. But on the other hand, we have no more space on heap to introduce any more new objects. We're spending a lot of time doing GC, and we can't even increase our throughput due to our heap being so full. If we could reduce the amount of space our cache was taking up our heap, we'd solve all of these problems, right? So the last thing you usually want to do when you're trying to optimize latency is store a large part of your working set on disk. Reads from disk can be times 10 to times 100 slower than reads from memory. But in our case, we knew that a creator cycle could take minutes to hours. And even though it reads a large amount of data from disk, it would be reading only once. And so the overall impact and the entire cycle duration would be negligible, especially since we can even prefetch the data and wait even less. And so we put 70% of our cache on disk and only 30% in memory. That caused our cache get duration to be a little higher. But on the other hand, we freed most of our heap. And so we were spending a lot less time doing GC. And due to that, our overall application latency was now faster. And due to the fact we cleared up all this heap, we were able to increase the number of threads. And by that, increase our throughput as well. So back to this. We improved our cycle duration by 50% by introducing this new cache. By then moving most of it to our disk, we were able to increase the number of threads and improve our throughput by another 30%. So happy ending. We're happy with our cache. It's taking up minimal space on heap while maintaining a high hit rate and keeping our data fresh. We ended up reducing our latency by 50%, increasing our throughput by 30%, and we had data to show us exactly by how much revenue we've improved. And to our key takeaways, We discussed async profiler and its advantages over others. Tools to be used when dealing with memory issues, like the very verbose heap dump versus the lightweight memory histogram. We talked about lambdas and why they're not innocent. They keep the reference to the object that you pass to them. Trove collections and primitives over wrapper objects have a large impact when running at scale. Cache effectiveness versus heap. When our cache was too big, our heap died, and so did our application. And when we tried to free up some heap, we limited the cache's size and lost its effectiveness. And so our application was slow again. And last, disk is your friend. Even though it's usually counterintuitive, at times you want to consider using it. Thank you.